Hi guys, welcome to today's tutorial. Today we're going over the worksheet number 8 and I'm gonna go over the question 3 here specifically. So let's get started. Question 3. Okay. So what question 3 says here is to find the absolute maximum and minimum of the following given functions on the given intervals, and make sure to justify the condition of the extreme value theorems. So before we go over each of these questions, let's just review what this extreme value theorem is here. This theorem says that if a function f of x is continuous on a interval, closed interval a and b, then it must attain a maximum and a minimum. Each at least once. So it means that it must, must have maximum and minimum. That means there exists a point inside this closed interval a and b such that if you plug in this point into the function, it is the maxed output of all the numbers you put in. And there's another point inside this interval for which if you plug in, then it is the least value of the outputs. Okay, so the condition here for the extreme value theorem, it is that the function f of x must be continuous, and it must be continuous on a closed interval. So these two points are very important. Must be continuous first, and the interval has to be closed. If you have an open interval, then it doesn't work, right? So make sure to check these two things, continuous and closed. That is like the key point. So now after understanding the theorem, now let's go over each of the questions. Number A, I have f of x equal to exponential function e to the negative of x minus e to the negative of 2x defined on the interval 0, 1, right? We know that this is a subtraction or a difference of two exponential functions, right? And each of the exponential function, it's already known to be continuous, right? So the subtraction is also continuous. So we know that this f of x is continuous on this closed interval 0, 1, which satisfies the extreme value theorems, right? Let's be more specific. Put it here. And now let's be more specific about that. For the function a, here, the function it's continuous on the closed interval because exponential functions, they are always continuous. Okay. The next thing to do is to find out the absolute maximum and the absolute minimum here. How do we do that? We know that firstly we need to find all the critical numbers, because the absolute max and absolute min, they occur either at the critical numbers or at the endpoints. So we're going to find all the critical numbers, and then we're going to plug them in into the function to see what kind of outputs, what kind of value we could get. And also we will need to plug in the endpoints of the interval. In this case, that will be 0 and 1. And among all the outputs, we compare the values to see which one is the max, which one is the min, and that is our absolute max and absolute min. That is the technique. So let's find the critical numbers first, right? To find the critical numbers, we need to be mindful that there are two kinds of critical numbers. One kind is those where the derivative is equal to 0, right? And the other kind is where the derivative does not exist or undefined. So right here, to find critical numbers, we need to figure out where the derivative f of x is 0 or undefined. Okay, so that's two kinds of critical numbers. So write out the derivative, right? Just straightforward by using the exponential rule and the chain rule, right? So it's negative is e to the negative x times negative 1 for the first one, minus e to the 2 minus 2x times negative 2, right, by the chain rule, which is equal to, 2 times e to the negative 2x minus e to the negative x. Right? And now we're gonna set this to 0. Right, so we have a kind of equation to e negative 2x minus e to the negative x equals 0. Right? We're going to solve this equation to find out the solutions. Those are the points where the derivative is equal to 0. So what we do here is to factor out the e to the negative 2x, or you can think about like multiply e to the 2x on both sides. So we're going to do this way since that is simple. So e to the 2x multiply on the right and on the left, right? And the right side is always 0, right? What we have on the left is e to the 2x multiplied with e to the negative 2x. That becomes just 1. Cancel out with each other, right? So we have 2, right, minus e to the x, right, still equal to 0. Right? So that we have e to the x equal to 2, right? And we solve this just to take the log on both sides, take the ln, so x is equal to ln2. Okay, so is this a critical number? Well, it seems that we're missing something, right? For this thing to be a critical number, we need to make sure that this number is inside our domain. In this case, should be the interval 0, 1. If it's not inside the interval 0, 1, that is not under our consideration, right? So we need to make sure that is this inside the 0, 1. And indeed, it is, because 1 is equal to ln e, right? And we know that 2 is less than E because E is approximately 2.71 something, right? 2.71 something, which is greater than 2. And we know that ln is a function, increasing function. So the greater the input, the greater the output, right? So you see that 2 is less than E. The input is less, right? So the output is less. So this thing is like less than ln which is equal to 1. So we know that this thing, ln2, it is inside the interval 0 and 1, and therefore is one of the critical numbers. And it is the only critical number where the derivative is equal to 0. And are there any kind of critical numbers? Because we know the other type is when the derivative is undefined. Right? There's no such critical numbers because this derivative is always defined, right? This derivative here, it's always defined. For what kind of value you plug in, it always gives you a defined output. So it's always defined, always exists. Okay, so that is the only critical number we have. That is x equal to ln2. Right? I have said that rather than testing the critical numbers, we also need to test the endpoints 0 and 1. And therefore, we have 3 points to test, right? These points are ln2, 0, and 1. Hence, we test 0, ln2, and 1. We plug this number back into the function one by one to check the output. So pay attention here, we are not plugging these values into the derivative. We are plugging this function into the original function because we want to see the value of the function, not the derivative function. So pay attention to that. Plug this back into the original function, not the derivative, because we want to see the value of the function, that is the min or max, right? So plug them in. So plug in 0 first. f0 is equal to, what is the function? The function is e to the negative x, so right, so e to the negative 0 minus e to the negative 2 times 0, which is, 1 minus 1, which is 0. Plug in ln2, so that is e to the negative ln2, right, minus e to the negative 2 ln2. That is equal to e to the ln2 to the negative 1, right, minus e to the ln2 to the negative 2. And we know that e can cancel with ln, so this is 2 to the negative 1 minus 2 to the negative 2, which is, 1 over 2 minus 1 over 4, which is 1 over 4. Right, so the second value, the second output here is 1 over 4. The last one that we need to test is f1. So e to the minus 1 minus e to the minus 2 times 1, right? I always forgot the function. Yep. That is 1 over e minus 1 over e squared, and if you do the common denominator, then it becomes e minus 1 over e squared. Right. So this value is a little bit tricky, right? But we know that e is, approximately 2.71, right? So e minus 1, it's approximately 1.71, something like that. And if we divide this number by, e squared is already, e is already greater than 2, let alone e squared. If we divide this 1.71 by e squared, we will obtain a value that is very, very small. So let's write that out. E squared is approximately 7.29, right? So if we do this kind of division, that is approximately to 1.7 over this 7.29, which is less than 1/4, you can see. Right? So we don't care what this value exactly is, as long as we know that it's less than 1/4 is enough, because we want to just find the max number among these three numbers, and also the least value among these three numbers. And as we can see, the least one, the smallest one is 0, and the greatest one is 1/4, right? And this something, e minus 1 over e squared, is kind of in between these two values, right? So we don't care about it at all. We've already had that the maximum value is 1/4 and the minimum value is 0. So now let's give our conclusion here. Therefore, the function fx has this the maximum, it's 1/4 at x equal to ln2, and the minimum it's 0 at x equal to 0, right? We have found the absolute max and absolute min, and we have pointed out where they are. One of them is at x equal to ln2, and the other is at x equal to 0. So that is our, question A. And now let's move on to the question B. Okay, so the same setup, right? We need to check the extreme value theorem. We don't need to change much in here. We just need to change the statement, because well, g of x here is a polynomial function, right? So it's always continuous. So what we need to change is just this part here, because polynomial functions are always continuous. Let's change this word to polynomial. Okay, so we have checked the extreme value theorems. This function is continuous on this closed interval -1 and 2. To find the critical numbers, we need to figure out where the f prime x is 0 or undefined. So the same setup, we just need to change the function here, right? Change this thing here. So the function we're working on is this g of x. If we when we find the derivative, we need to apply the chain rule at the first step. So that is 3 times x2 minus 1 to the 2 times the derivative of the second layer, which is 2x, right? And we know that this is still a polynomial, so it's always defined, right? So nothing to change, just change this small thing. And then we do the same thing, set the derivative to 0. Okay, so set the derivative to 0. We will have 3x squared minus 1 to the 2 times 2x equal to 0, right? So now we have a product equal to 0. So it's either one of the factors equal to 0. So it's either x squared minus 1 squared equal to 0, or 2x equal to 0, right? Which implies that x squared is equal to 1 or x is equal to 0, right? And if we solve them, we have, three solutions: x equal to positive negative 1 or x equal to 0, right? So we have like three different numbers: negative 1, positive 1, and 0. Are all of these numbers critical numbers? We don't know. We need to see if they're in our domain. In this case, the domain is from negative 1 to 2, right? So all of these numbers are inside this interval. All of them are inside this negative 1 and 2, right? So all of them are critical numbers, okay? So we need to test the critical numbers as well as the endpoints. So you can see that in this case we have actually 4 points to test, right? So we need to test all the critical numbers. We need to test, in this case, negative 1, 0, 1, and the other endpoint, which is 2, right? So we need to test these numbers. So let's do them. Delete here. The function was gx equal to that x squared minus 1 to the 3. So test negative 1 first. That's equal to negative 1 squared minus 1 bracket to the 3. So that is equal to 0 minus 1 to the 3. 1 minus 1 to the 3, which is 0. Right? And we also plug in g0, that is 0 squared minus 1 to the 3, which is negative 1 to the 3, which is negative 1. Right? And test 1, g1, that is 1 squared minus 1 to the 3, which is also 0. And the last one is 2. Test it. 2 to the square minus 1 to the 3. That is 4 minus 1 to the 3, which is 3 to the 3. That's 27. Okay, so that is a huge number, right, among all the outputs here. Now, obviously, the greatest output among these numbers it's 27, which will be our absolute max in this case, and the least number we've got here is 0, which will be our minimum in this case. So let's just finish the statement here. The statement here. Therefore, the maximum here is 27. Let's change this thing here. 27 at x equal to 2, and the minimum is 0, not 0, negative 1. It's negative 1 at x equal to 0. Okay, negative 1 is the smallest and 27 is the greatest. That is pretty straightforward still. Let's just follow this setup to finish the last question. Okay, I forgot to change this to B. Okay, so going to the last question, still follow the same setup, right? Just change the content. Okay, question C here. H of x. This function is continuous on this closed interval because it's a subtraction, right? Both of which are continuous for x greater than 0. So let's be more specific, because the polynomial functions and so let's change the statement here. The polynomial functions and logarithm functions are always continuous for x greater than 0. Why do I say x greater than 0? Because if x is less than or equal to 0, then the log function is not defined. So we must make sure that is greater than 0. Well, however, the interval given here is from positive 1 over 2 to 2, which is already greater than 0. So we don't have that kind of concern that the function is not defined. Right? The function is defined on this interval, and we know that is continuous because of this statement is a subtraction, right, of two continuous functions. Now we have checked the extreme value theorem. Now the next step is to find all the critical numbers, right? To find them, we need to figure out that there are two types. One type is when the derivative is equal to 0, right? It is f prime of x. I should change that to h prime of x in this case. Right? We want to know when this derivative is equal to 0 or undefined. Okay, so let's kind of work out this. H prime of x is equal to 1 minus 1 over x, right? This thing is always defined except x is equal to 0, right? So we need to just change this slightly, which is always defined on this 1 over 2 and 2. That is enough. We know that it's not defined as 0, but 0 is not inside this interval, so we don't care. We just need to make sure that this is defined on this interval. That is already enough, right? Which means that we only have the other type of the critical numbers. That's when the derivative equal to 0, right? We don't have that type when the derivative does not exist. Okay, so set the derivative equal to 0, then h prime of x is equal to 0, right? So we have here 1 minus 1 over x equal to 0, and we multiply x on both sides, so we have x 1 minus x times equal to 0 times x, right? So we have x minus 1 equal to 0, which means that x is equal to 1. So this number x equal to 1 will make the derivative equal to 0. But before stating that this number is a critical number, we need to make sure that it's inside our interval. Is it inside the interval? Obviously it is inside this, right? And therefore it is a critical number, right? So we need to test this number as well as the endpoints, right? So we're gonna test this time, test 1, right? And the two endpoints here, that's 1 over 2 and 2. Just plug in and test. So delete all these things here, follow the same setup, right? We test 1 over 2 and 2. And I want to emphasize here again, when you are testing these points, you are plugging these points back into the original function to test, not the derivative. Remember, the original function. Okay, so do that. So we have h of 1 first, that is 1 minus, right, ln1. We know ln1 is 0, so it's 1 minus 0, 1. And test 1 over 2, okay, so that is 1 over 2 minus ln of 1 over 2, right? What is that? Minus ln of 1 over 2. ln of 1 over 2 is, we know ln 1 over 2 is kind of 2 to the negative 1, right? So by the property of the log function, we were able to, put this to the front, right? Do something like this. So this is actually equal to 1 over 2 minus 1 ln2, which is 1 over 2 plus ln2, right? Let's continue to test the other one. h 2 that is equal to 2 minus ln2. Okay, right? So we have these three numbers here. The first one is 1, the second one is 1 over 2 plus ln of 2, and the other one is 2 minus ln of 2. And we need to determine which one is the greatest and which one is the smallest. We will need a calculator to do that. Actually, we can figure out this without a calculator, but that might be very complicated. So just pretend that we have a calculator right now. I know that on the exam you're not allowed to use the calculator, but well, in the exam you won't see a question like that. I mean, the output is always decidable by without a calculator. Just pretend that we have a calculator right now. ln2 is approximately 0.69. Okay, right? So we see that this value here is approximately what is that? It's anyway greater than 1, right? It's greater than 1, less than 2. So this thing less than 2. About I would say about 1.19, right? And this value is about approximately 1.31, right? And this is 1. So we see that the maximum value here should be 2 minus ln of 2, and the minimum value here should be 1. So finish the statement, copy and paste, right? Therefore, the maximum is this guy, right? 2 minus ln of 2 at x equal to 2, right? Still x equal to 2. And the minimum value is just 1, right? At x equal to 1. Okay. This is the min here, and this is the max. Okay. The max, this is the min. 1 and 2. Okay. So that is this question C. And if we compare the solution format of these three questions, we found actually the exact same pattern here. Firstly, first step is to check the extreme value theorem, check that the function is continuous, defined on a closed interval. That's very straightforward. And the second thing is to find all the critical numbers. Remember, there are two types of them. If the derivative always exists, always defined, then you need to only find the first type, which is when the derivative is equal to 0. That's called critical numbers. When you obtain these numbers, make sure that they're inside the domain, so they're indeed the critical numbers. If it's not inside the domain, then we reject them, right? And after having the critical numbers, put them with the endpoints together, list them here, and you plug them in back into the original function to test the output, right? And among all the outputs, you compare the values and select the greatest one and the smallest one, and claim that the max occur at that point. Well, just check the inputs there, and the min occur at the other point, and also check the input there. And that is the format of solving this. Actually pretty straightforward. So that's it for today. I hope that you enjoy this tutorial, and good luck to your next test. So that's it for today. If you like my videos, make sure to subscribe to my channel. I'll make more videos about that in the future. So see you guys in the next episode.